Have you ever looked at a simple line of code on a screen and wondered how on earth that becomes a physical, high-performance microchip? The tiny silicon brain inside your phone or computer? Well, today, we're going to follow that incredible journey from a software idea to actual silicon and unpack the massive challenges engineers have to solve to make it happen. So, on one side, you've got something that looks pretty simple, right? A straightforward function in a language like C++. But on the other side, well, that's the reality of a microchip. It's this incredibly complex web of logic gates and registers. So the big question is, how do you get from this simple instruction on the left to that intricate, timed piece of hardware on the right? Well, that chasm between the two is what we call the implementation gap. You see, it's the difference between an abstract, untimed description of what a program should do and the timed physical blueprint describing how it's going to do it, all synchronized to the nanosecond ticks of a clock. To put it simply, the software idea has absolutely no concept of time, but the hardware, it lives and breathes by it. So here's our roadmap for this journey. First, we're going to define our destination, the chip's blueprint. Then we'll explore 3 totally different paths engineers take to get there, including one that uses what I call digital Legos and another that uses AI. And finally, we'll get into the really tough choices every single designer has to make. Okay, before we can even talk about bridging this gap, we need to understand what's waiting for us on the other side. We've got to know our destination. And in the world of chip design, that destination is the hardware blueprint we call RTL. RTL stands for Register Transfer Level. I want you to think of it like the chip's super detailed architectural plan. It doesn't just say, hey, add these numbers. Oh no, it describes the precise flow of data between these tiny, high-speed storage spots called registers, and it details the exact operations performed on that data at every single tick of the clock. And any RTL design really has 2 main parts. First, you've got the data path. This is where all the action happens. It's packed with the calculators, like adders and multipliers that do the actual math. And then you have the control path, which is kind of like the traffic cop. It's in charge of directing the flow of data, telling all those calculators what to do and exactly when to do it. All right, so now we know our destination, this detailed RTL blueprint. The next question is, how do engineers actually create it from just a high-level idea? Let's check out the 3 main ways they bridge that implementation gap. So the first path is manual coding. This is the artisan approach, where every single line of RTL is painstakingly handcrafted. The second is called IP assembly, where designers act more like master builders, piecing together pre-made, complex blocks, or digital Legos. And the third? That's behavior synthesis, which is like having an AI architect that automatically generates the whole design from a simple description. Now, in modern chip design, it's really the last 2 approaches that dominate the landscape. IP assembly starts with existing, already verified hardware blocks and is all about integrating them into a bigger system. Behavior synthesis, on the other hand, starts with a pure algorithm and automatically generates those hardware blocks from scratch. They're 2 very, very different philosophies. Let's start with the most common method in the industry today, IP assembly. This is really the art of building these massive, complex systems by snapping together pre-built, reusable components. This whole approach is the heart of what's called a system on a chip, or an SoC. And it's exactly what it sounds like, an entire computer system with its processor, its memory, its peripherals, all squeezed onto a single piece of silicon. The chip inside your smartphone, that's a perfect example of an SoC. So why is this so popular? Well, for starters, it dramatically boosts productivity. Designers are integrating, not reinventing the wheel every time. This reusability slashes development time and costs, and it lets companies pack an incredible amount of features, like a CPU, a GPU, and an AI accelerator, all onto one tiny chip. The building blocks for these SoCs are called intellectual properties, or just IPs. These are the digital Legos we were talking about. An IP can be anything, really, from a complete processor core you license from another company to a memory controller your team built. The key is they are pre-designed, pre-verified, and ready to be dropped into a new design. But, and this is a big but, it's not as simple as just snapping Legos together. First off, each IP block has countless parameters that have to be configured perfectly. Second, connecting hundreds of these blocks requires a really sophisticated on-chip network. But honestly, the single biggest hurdle is verification, making sure this massive integrated system of independent parts actually works together flawlessly. That is a huge task. Okay, so now let's look at a completely different way of thinking. What if, instead of assembling pre-built blocks, a smart tool could automatically create the entire blueprint for us? Well, welcome to the world of behavior synthesis. Behavior synthesis, which you might also hear called high-level synthesis, is a process where a tool takes an untimed algorithm, our abstract idea, and just automatically translates it into a fully timed RTL design. The designer gives it constraints, like make it small or make it super fast, and the tool then explores countless options to find the best possible blueprint. It's pretty amazing. To see just how powerful this is, let's take an incredibly simple algorithm, just adding three numbers together. I mean, it seems totally trivial, right? But how many different ways can you actually build a circuit to do that one simple thing? Let's see what the synthesis tool comes up with. So the tool can generate several completely distinct designs. The first one, RTL1, uses two adders in a chain. Boom, gets the result in one clock cycle. RTL2 also uses two adders, but it adds a temporary storage step, a pipeline, in the middle, so it takes two cycles. And then there's RTL3, which gets really clever. It uses just one adder, twice. It also takes two cycles, but it saves a ton of space. Now, this is where it gets really interesting, because this reveals all the trade-offs. RTL1 has the lowest latency. It gets you the answer in a single cycle, fastest response time. RTL2, the pipelined one, can run at the highest clock speed, making it the fastest in terms of raw throughput. But look at RTL3. By reusing its adder, it is by far the smallest and most cost-effective. You can see right away, there's no single best option here. So the huge power of behavior synthesis is that it automatically explores this massive design space, finding clever solutions a human engineer might just miss. But it's not perfect. The code it generates is often really, really hard for a person to read or debug. And sometimes it can create a design that looks great on paper but causes what are basically traffic jams or congestion on the actual chip layout. So, we've seen two powerful but very different ways to bridge that implementation gap. And this brings us to the final, crucial question that every single chip architect faces. How do you choose the best path forward? And this just brilliantly illustrates the point. There is no single best design. The choice is always a trade-off. If your application demands the absolute fastest response time, you pick the design with the lowest latency, like our RTL1. If you need the highest possible clock speed for throughput, you go with RTL2. And if cost and size are what keep you up at night, you choose the smallest design, RTL3. So the key takeaway here is that chip design isn't about finding one perfect solution. It's really the art of balancing these competing constraints, performance, power, and area, to create the optimal blueprint for a very specific purpose. The right answer for a smartwatch is definitely the wrong answer for a supercomputer. And this all leaves us with a fascinating final thought. As these automated synthesis tools become even more powerful, even more intelligent, is the job of a human chip designer going to change? Will they become less of a hands-on creator and more of a high-level curator, guiding these AI architects to find that perfect balance for the next generation of technology? It's something to think about.